Hello everyone. As promised, I'm going to go through a few of my extra slides that go along with lecture 10, just to give you a little bit more exposure to the application of Newton's laws in the case of ideal ropes and pulleys. So in this example problem, we have an incline with a pulley and there are two masses, one of mass 2m and the other of mass m. And they are on an incline with an angle of 35 degrees. But we are asked to find the acceleration of the boxes when the system is released, and we're told that friction is negligible. Of course, in lecture 11, we introduced the idea of friction. In this problem, we are considering a situation where friction is absent. So the question is asking for the acceleration of the boxes in plural, and this is important to note, and I've mentioned this during our lecture. Both of these boxes must have the same acceleration because they're tied together by this rope, and since we are assuming an ideal rope, there's no stretching, and so whatever acceleration the one box has, the other box will follow. Now, whenever you're solving a problem like this, even if you think you've got mechanical intuition, it's good to solve the problem formally by following the proper steps. And the first step, of course, is to draw free body diagrams for both of the boxes. Well, for each of the boxes, one of the forces acting on the boxes is gravity. So in the case of the blue box, we have mg pointing straight down. And in the case of the beige box, with mass 2m, we have 2mg pointing down. Both of the boxes are also experiencing tension, albeit in different directions. In the case of the blue block, tension is pointing directly up along the rope, and it is in the direction opposite the weight of the blue block. And in the case of the beige or orangish block, tension is going diagonally up the incline, which is not directly back-to-back with its weight, although, as we'll see, it is back-to-back with the parallel component of its weight. The other force operating on the beige block is the normal force pointing up. The next thing you have to do is you have to select your axes. In this problem, we are going to have the x direction, the positive x direction. For the beige box, it's going to be going down the incline, which means that for the blue block, going up is the positive x direction. And again, for the beige block, we have both a y component, or a perpendicular component, as I like to call it, and a parallel component, an x component. And again, we have to be consistent. When this block is going up, this block is going down or to the right, and that is our positive x direction. Finally, we need to write out Newton's second law for each of these cases. So for the blue block, our equation is that the tension minus mg equals ma. For the beige block, we have two sets of equations, one in the x direction and the other in the y direction. In the x direction, we have that 2mg sine theta, which is the component of the weight that is parallel, that is in the x direction, pointing down the wedge, minus the tension, which is in the opposite, in the negative x direction, equals 2m, the mass of the block, times its acceleration, a. In the y direction, we have that the normal force minus the y component of the weight, that is perpendicular, which is 2mg cosine theta, that has to equal 0 because there's no acceleration in this direction. Now, at this point, you might not be sure which way the acceleration is going to go. And on some level, that is okay, because we have been consistent in writing out these equations with making the positive x direction go this way, and for the blue block, the positive direction is this way. And we have written out our equations correctly, and so if the beige block ends up accelerating to the left, we will get a negative acceleration, and if it accelerates to the right, we will get a positive acceleration. And so as long as we are self-consistent, this equation will take care of our solution. Now, you might think, well, this block is more massive than this block, therefore it will go down. But of course, the incline has a fairly, shallow angle. And so the component of the weight pointing downward might not be enough to overcome the tension. And so it is perfectly reasonable to assume that you don't necessarily have a good mechanical intuition on what this is going to do, and really just go through the problem and solve it. So we don't care too much about the y component here. As we saw in lecture 11, the y component, of course, matters for friction because the friction is proportional to the normal force. But since we have no friction here, we know that the normal force and the component of the weight of the block perpendicular to the surface cancel each other out, and that's all we really need to know. But the 2x equations are, of course, very important, and we have two equations, and those two equations are in two unknowns. We don't know the tension or the acceleration. And so now we need to solve these two equations. Well, we can add mg over to this side, and we get that tension equals m times g plus a. And then we can substitute this expression for tension into the second equation so that we get 2mg sine theta minus m times g plus a, the tension, equals 2ma. And now it's just a matter of solving the algebra. Now, one of the things that you could do that these slides don't do is you could plug the numbers in sooner. But we know g, we can approximate that as 9.8 or 10 meters per second squared, and we also know the angle theta is 35 degrees. But what these slides do, and what I tend to like to do, is to sort of symbolically solve the algebra and then go back and plug the numbers in at the end. And so let's simplify this. We've got we can divide this equation both sides by m, and all of the m's cancel, so we get 2g sine theta minus g minus a equals 2a. We can add this a over to this side, divide by 3, and we get that a equals g over 3 times 2 sine theta minus 1. And then we can, of course, plug in the specific numbers, and we end up getting 0.48 meters per second squared. Notice that the acceleration is positive, so it is indeed the case that the block is sliding down the incline. The beige block is sliding down the incline. But it is worth pointing out that our angle was 35 degrees. If our angle was less than 30 degrees, A would have been negative. The beige block would have gone up the incline as pictured here. So if theta drops below 30 degrees, the component of the weight of this block in the parallel direction is not enough to overcome the tension force on it, and then both of these blocks accelerate this way rather than down. But of course, in this problem, where it was 35 degrees, they both accelerate towards to the right in the x direction. The blue block goes up and the beige block goes down. Now, this can be easier if we don't care about the tension. We can write Newton's law for the whole system, bearing in mind that these things are accelerating together. We have the x direction, we have 2mg sine theta minus mg equals 3m times the acceleration of the two block system. Okay, so we have mg is pulling on the two block system this way, and 2mg sine theta is pulling on the system this way, and the mass of the total system is 3m. So we could plug the 3m there and then just write out the equation, and that would have given us the same solution. Now let's do another example. This is a double incline. We have a box of mass m1 equals 1 kilogram sitting on a double incline attached to another box of mass 2 kilograms on the other side of the incline, held together by an ideal string that goes through an ideal pulley. Again, ideal pulley means that the pulley is massless and that there's no friction, and an ideal string is that the string is massless or of negligible mass, and it doesn't stretch. So the angles between the two inclines of the horizontal are 30 degrees on this right side and 45 degrees on the left side. If the inclines are frictionless, what is the acceleration of the system? So let's work on the problem. As always, take a deep breath and write down what you know. We know the masses, 1 kilogram and 2 kilograms. We know the angles, 30 degrees and 45 degrees. Step 2, draw the free body diagrams. The weight is pushing down. The normal forces are pointing perpendicular to their respective surfaces, and the tensions are pulling in opposite directions, up and to the left in the case of the blue box, and up and to the right in the case of the red box. Note that a bigger mass and steeper slope on the left suggests that it will move to the left. So for this problem, because we do have an intuition about how this is going to go, we're going to call the positive x direction the left. Now, if our intuition is wrong, as long as we are consistent, then we would get a negative acceleration as the answer. But as you'll see, our intuition is not wrong. But if it is, what's nice about this is we can afford to be wrong. We are positing that the positive x direction is going to the left, and then we will see what the sign of the acceleration in the end is. Well, for both of these cases, we do have to consider the projection of the weights of the blocks, both in the directions perpendicular to the incline and parallel to the incline, and that's true for both blocks. And then we can write out our equations. We are, of course, going to neglect the y or perpendicular components in both of these problems because, again, without friction, it's not really relevant to the problem. And what we get is t minus w1x. So t is going in the positive direction for this block, and w1x is going in the negative direction. That's the x component of the weight of block 1, equals m1a. And for the red block, we have that the weight of the red block is going in the positive x direction. So that's positive minus the tension, which is going in the tension is going in the negative direction, equals m2a. And then we can plug in for w1x and w2x that those are equal to mg sine theta, respectively. So this would be this would be m1g sine theta 1, and this would be m2g sine theta 2. And when we solve this system of two equations, we end up getting that the acceleration equals g times m2 sine theta 2 minus m1 sine theta 1 divided by m1 plus m2, which equals 0.31 times g, which is 3 meters per second squared. And because this answer is positive, that means that the acceleration is going in the direction of the positive x-axis, which we put to the left. And so it turns out our intuition is correct, that it does accelerate to the left. Now, if we were to adjust these angles, we could come up with a scenario where the whole system accelerates to the right, but that is not the case here. We had an intuition, we picked a coordinate system, we were completely consistent in writing out the equations, and when all was said and done, we got an answer that was positive for the acceleration, meaning that the acceleration was indeed in the direction that we designated as the positive x direction.